Okay, so in this movie clip, we're going to study the junction breakdown. So usually, the breakdown cannot be expected in the ideal diode. So basically, the ideal diode can never get any type of a breakdown. But in practical PN junction diode, the breakdown can be occurred under reverse bias. More specifically, under a certain very strong reverse bias, the junction can be broken down. In other words, exponentially increasing current can be flown across the PN diode. So uh, as graphically shown in this current versus voltage characteristic of junction diode, at a certain reverse bias denoted as a V sub BR. BR indicates breakdown. The current flow can be exponentially increasing. So as we have learned, under forward bias only, the current can be exponentially increasing in PN diode. However, don't forget that the current can be exponentially increasing under reverse bias as well, but that breakdown voltage should be much higher than the built-in potential or built-in voltage. Okay, usually that is 0.7 volt, but this breakdown voltage is usually minus 5 volt or even higher. Okay, so approximately 10 times difference. Okay, then the next question to come up with is, what is the main application of this junction breakdown leakage current? To protect any unwanted current flow into the integrated circuit chip, so Zener diode can be used as an electrostatic protection circuitry. So simply with one resistor and one Zener diode, well, here in the instead of diode, we're saying it as a Zener diode. That means the Zener diode has been designed originally on purpose to operate in the breakdown mode. Again, the Zener diode is originally designed to be worked in the breakdown region. So this Zener diode can be worked in this regime. So always Zener diode, the normal operation for integrated circuit chip, the Zener diode should be, you know, say the current should be flown into the integrated circuit chip and flown out of the IC chip. That is normal operation. But as for because of for some reason, for a known issue, the current can be reversely supplied into the IC chip. This would be kind of disaster. This would fry up your IC chip. So we should protect this unwanted current flow into the IC chip. So on that purpose, the xenon diode should be turned on when the unwanted current has been allowed into the IC chip. So this unwanted current should be flown throughout the xenon diode. So xenon diode can be acted as a bypass for the unwanted current flow. Okay, so in normal operation for IC chip, the xenon diode cannot do anything. However, unwanted current can be one can be flown into the IC chip. Then xenon diode should be turned on. Then IC chip can be protected. Okay. So now let's get into some more details how to understand the breakdown voltage denoted as V sub BR. So as described in the lecture note, if the reverse bias voltage, say minus V sub A, is so large, okay? Herein again, so large. I mean, the more quantitatively speaking, maybe higher than, the magnitude of the reverse bias voltage should be higher than built-in potential, okay? Usually 1 volt. Then the peak electric field exceeds a critical value denoted as electric field E sub CR critical. Then the junction will break down. The physical meaning of breakdown is large reverse current flow can be formed. Okay, so breakdown doesn't mean the physical breakdown. The breakdown happened in PN junction diode means the unwanted humongous amount of current flow can be formed from N to P. Usually P to N, large forward bias, forward current is allowed, but it's definitely straightforwardly you may guess that large reverse current can never be allowed, but it is flowing. What would be happened? Yeah, the PN junction diode should be broken down. Okay, so this critical electric field has can be derived, but I won't explain all the details. So in your textbook, page 266, there is a full derivation steps for this equation. So please take your time how to derive the critical electric field. Okay, so this is a critical electric field when the applied voltage is identical to the breakdown voltage. Okay, and herein the N indicates 1 over N is equal to the 1 over ND plus 1 over NA. Definitely this ND is a donor's concentration in N side, and this N sub A indicates the acceptor concentration in the P side. So this N indicates a lightly doped side 1 uh, electron or hole concentration. Okay, so plugging in the ND or NA into N, and you know the built-in potential once you know the ND and NA, and dielectric constant, unit charge, and breakdown voltage, then you may estimate the critical electric field. So from this equation, you may reversely obtain and derive the breakdown voltage as well. If you know the critical electric field, then you may estimate the breakdown voltage. Okay. So herein, this N is inversely proportional to the breakdown voltage. So you may guess that this is PN diode. So say case number 1 is here N sub A is 10 to the 18, here N sub D is 10 to the 17. Case number 2 is here N sub A is 10 to the 16, N sub D is 10 to the 15. Which case would give you a higher breakdown voltage? Which one? Diode number 1 or diode number 2? Again here 18, 17. Case number 2 is a 16, 15. Which one give you high breakdown voltage? Number 1 or number 2? Yes, number 2. Because here, just take a lightly doped one here. In case number 1, take a lightly doped side 1, so 17, 15. Then plug in here, and which 10 to the 15 would give us the higher breakdown voltage. Okay, so if you draw the or imagined IV characteristic, case number 1, and here case number 2. Okay, so much higher breakdown voltage, the breakdown event would be happened in case number 2. Okay, then now let's dive into some more physical details, how the breakdown can be happened in the PN junction diode. So basically breakdown can be happened under reverse bias. So once you draw the energy band diagram for the p-n junction diode, since again the plus V, right? So now the P side is relatively lower voltage applied into the P side so that E sub F in P side and E sub F N side. So this energy difference should be corresponding to the applied voltage. Well, definitely EFP is higher than EFN, so VA is negative. So that's the reason why I have used the magnitude of Q times VA. So once this Q times VA is not too high, I mean the very small, then the minority carriers in the P side and minority carriers in the N side would get into the depletion layer and it would move by going through this animatically shown uh, energy change in the depletion layer. Okay. However, once this energy difference between EFP and EFN, take a look at how high it is. Yes, this amount of huge high reverse bias has been applied across PN diode. Then some very interesting events would be happened. Let's suppose that a single electron has been injected into the depletion layer. Okay, so here in this is x of minus xp, the depletion layer edge on the p side. So a single electrons would be thermally generated in this region. I mean in the range of minus xp and minus xp minus ln. So in this region, electron hole pairs are thermally generated, and there is possibility for the thermally generated electron to be diffused toward the p-side quasi-neutral region or uh, into the depletion layer with a 50% probability if we are taking into account the x dimension only. Then thermally generated electrons would diffuse to the left-hand side or right-hand side. So this thermally generated electron would move toward the depletion layer, then it would be exposed and drifted or accelerated because of the electrostatic force coming from the built-in electric field in the depletion layer. So think about the force is defined as minus Q times electric field. So due to the built-in electric field, the negatively charged electron would be forced and then accelerated. So acceleration means it would gain its own kinetic energy. Okay, so in the energy band diagram, the kinetic energy can be illustrated between two energy difference, E sub c and the electron's energy. So this. So as electrons are accelerated because of the built-in electric field, and it would gain it would gain lots of kinetic energy. But at some point, suppose that here the electron would be scattered out because of the phonon. So phonon, what is the phonon? Phonon is a vibrating silicon atoms. So since this free electron or conduction electron is freely moved in the silicon lattice structure, which has which should be built up and named as diamond structure. So electrons would have some possibility to hit the silicon atoms in the lattice structure. So think about the heating event. Once accelerated electrons can hit the silicon atoms, what would be the velocity right at the moment of the heating event? Yes, zero. But as you know, the kinetic energy can be defined as 1 over 2 times effective mass of electrons times velocity square. But now velocity is zero, so the electrons which has been scattered and hit with the silicon atom should completely lose its own kinetic energy. But go back to the energy band diagram and think about that zero kinetic energy. How to express, how to illustrate the zero amount of kinetic energy of electrons which are hit and scattered with the silicon atom. Yes, no energy difference between E sub c and the energy level of electrons. So that we can simply say that the electron has lost its kinetic energy. This amount of kinetic energy has been gone, and electrons are moved downward herein. Let me change my color. Okay, here. And this lost kinetic energy can be delivered to the silicon atom. So suppose that there is a silicon atom. They are tightly bonded with the four neighboring silicon atoms actually, right? So the electrons which has participated in building up the covalent bond between two silicon atoms can be broken because of this kinetic energy. So here is a rule of thumb. How much kinetic energy should be lost to take out the electrons away from the covalent bonds? Yeah, the rule of thumb is that the kinetic energy which was lost because of the scattering event in the depletion layer should be equal or greater than 1.5 times band gap energy. So band gap energy of silicon is 1.12 electron volt. 1 electron volt is equal to 1.6 times 10 to the minus 19 joule. So once electron has been accelerated a lot and the scattering event has been happened in the depletion layer, and the kinetic energy that this electron has lost, which is greater than 1.5 times bandgap energy, then the electrons who has joined in the covalent bonding between two silicon atoms can be broken, and that electron would become free electron. So simply speaking here, I have used just a single electron has been diffused toward the depletion layer. But because of the high electric field, it has gained lots of kinetic energy, but there is no way for this accelerated electron to avoid any scattering event in the silicon lattice structure. So at some point, the accelerated electron would lose its own kinetic energy. But that lost kinetic energy has been well delivered to the electrons who has uh, stably existed in the covalent bonding between two silicon atoms. But that electron would break and becomes loosened, then it becomes, in the end, free electron. So a single electron would induce one more electrons, so total two electrons are available at some point within the depletion layer. And this mechanism can be repeatedly occurred again because of the stably formed built-in electric field in the depletion layer. So those two electrons would accelerate it together, and at some point, those two electrons would be scattered with the silicon atoms. Then the kinetic energy those electrons each has lost would be higher than 1.5 times bandgap energy. Then each electron would induce one more free electrons. Since we have two electrons herein, so total four electrons can be obtained. Then again, because of the stably formed electric field in the depletion layer, four electrons would be accelerated again, and at some point they're gonna be scattered and they're gonna lose their kinetic energy, and that lost kinetic energy would be delivered to the electrons which is still in covalent bond. then those additional 4 electrons would be generated. Then total 4 electrons are ready, available, and they're gonna be accelerated again because of the built-in electric field. So this mechanism breakdown kind of like the think about how many electrons can be obtained at each process. So let me erase my note here. So simply 1 electron has been injected into the depletion layer, but now 2 and 4 and 8, and afterwards 16, 32, 64, 128, 256, 512, 10, 24, and blah blah blah. So at the edge of the depletion layer, in the n side, I mean the x of xn, the total number of electrons available at x of xn is way more than the number of electrons injected into the depletion layer from the p side. So what is the minimum requirement for this breakdown mechanism can be happened? Yes, the kinetic energy here should be higher than 1.5 times bank gap energy. So to meet this requirement, the band bending should be very much. As shown in here, the band bending is very small. Then simply it's going to this electron would lose its kinetic energy, but that kinetic energy would be converted into thermal energy, and it doesn't do anything. So this electron would be simply falling down into the n side, and that's it. So very saturated current can be flown. Well, basically this is the basic idea of how the saturation current can be formed in the ideal diode. But now we are talking about the breakdown mechanism. Okay, so the minimum requirement to see the breakdown mechanism is this. And for that purpose, the P side and N side, the total amount of applied voltage should be higher than breakdown voltage. Okay, and that breakdown voltage can be written and expressed with this equation. And definitely the breakdown voltage is much higher than built-in potential. And herein the critical electric field, the intensity of critical electric field can be found within this range for the doping concentration 10 to the 14 to 18. So herein N indicates a lightly doped side carrier concentration. Okay. And the lastly, not but least, what is the meaning of avalanche? So avalanche means that a very small event has been happened on the top, but very kind of disaster can be occurred at the bottom. So this, looks like an avalanche happened in mountain. Okay, so this kind of similar physics can be found in the PN junction diode under reverse bias. So people are naming it as avalanche breakdown. Okay. All right, this is the one of the types to explain how come the exponentially increasing reverse current can be flown across the PN diode. Okay, so this is one of the mechanisms. The second mechanism to explain how the breakdown can be happened across PN diode uh, is a tunneling breakdown mechanism. But herein notice that the tunneling breakdown mechanism can be only valid and happened when both sides of the the P side and N side doping concentration should be heavily doped. I mean, the degeneratedly doped. Otherwise, tunneling breakdown mechanism can never be implemented. Okay? In other words, P side doping concentration should be higher than 10 to the 18 or higher, and the N side doping concentration is also higher than the 10 to the 18. Then we may expect the tunneling breakdown mechanism when we are explaining the exponentially increasing current flow under reverse bias. So herein, under thermal equilibrium, you know, p-n junction diode's energy band diagram has been drawn. But here notice that the E sub Fp is approximately identical to the balance band H E sub V. And here the Fermi energy level in the n side is approximately equal to the E sub C. Okay. And under reverse bias, so definitely the E sub Fp move upward and E sub Fn move downward, then you may draw the energy band diagram of heavily doped p-n junction diode under reverse bias. Then here in the depletion layer width, from here to here, W, is very narrow. So go back to the equation for depletion layer width, W. Once ND or NA are very high value, then this W is narrower than 10 nanometers. Then the electrons which are filling up the valence band, I mean the electrons which has participated in covalent bonding between two silicon atoms can move toward the empty state in the conduction band in the n side by tunneling mechanism. So basically, tunneling mechanism can, well, basically electrons can be described with a wave equation. So it's the electron is kind of rigid, solid ball, but in some other sense, the electron is kind of wave. So this wave can never be uh, defined at a certain single point. Wave can be, uh, can be existing at in a certain range instead of in a certain point. So for given 10 nanometer or even shorter depletion layer, the electrons in the p side edge would also exist in the n side as well. But from the perspective of classical physics, this solid, rigid ball or particle looks like, it seems that solid rigid ball would get through the depletion layer. Then people are naming it as tunneling. Okay, even though there is energy very high, just a small rigid stone can go through the energy barrier. So it looks like it can tunnel through, it can go through the energy barrier. Okay, all right. So as described here, when both sides of a junction are very heavily doped, the dominant breakdown mechanism is not avalanche breakdown mechanism, but tunneling breakdown mechanism. Or people are naming it as a Zener breakdown mechanism. So previously I said once the electron has been injected into the depletion layer and it would lose too much kinetic energy, so it would induce one more electron. So that mechanism can be happened in p-n junction diode when either side of junctions are heavily doped or neither of junction side is heavily doped. Okay, so again here the Zener breakdown mechanism is only valid when both sides of junction are very heavily doped. Okay, so now let's summarize what we have learned, and then from now on let's think about the breakdown voltage as a function of doping concentration in N side or P side. So you take a look at the solid line for silicon, and breakdown voltage has been drawn in log scale, 10, 100,000, and the doping concentration has also expressed in log scale along the x-axis. So breakdown voltage decreases with increasing N. So N is 1 over N is identical to the NA 1 over Na plus 1 over Nd. So I mean that this N indicates a light lit up the side carrier concentration. So as N increases, the breakdown voltage decreases. Why is that? Why is that? So you may imagine this. Pn. Case number 1, 10 to the 18, 10 to the 16. Number 2, 10 to the 16, 10 to the 15. Which one, which number would give us higher breakdown voltage? Yes, number 1. That is lightly dot side 1, and this 10 to the 15 is lightly dot side 1 in case number 2. Which one is higher? Yes, number 1. Once N is higher, breakdown voltage becomes lower. Okay, so case number 1 gives us a lower breakdown voltage. Case number 2 gives us a higher breakdown voltage. So to induce a breakdown mechanism in case number 2, we need more voltage. In case number 1, to obtain the breakdown event, we need a slightly lower voltage. Why is that? Physically speaking, why is that? Think about that, okay? So if you go to the page 266, you may intuitively understand the breakdown voltage, the magnitude of breakdown voltage becomes lower with increasing lightly doped side carrier concentration. So please do that. And in the second bullet, you may see that the breakdown voltage decreases with the decreasing band gap energy. So for given doping concentration, your band gap energy has been lowered, then breakdown voltage has also been lowered. Okay. So why is that? Please think about that. I guess you should explain it quantitatively or qualitatively. Both are okay. So please think about that. Go back to the avalanche breakdown mechanism and go back to the Zener breakdown mechanism and how breakdown mechanisms can be obtained and what is the minimum requirement for each. Then you may simply answer those two questions. So please do that. Okay. The last topic in this lecture, note 16, is a breakdown temperature dependency. So as temperature increases, V sub VR breakdown voltage increases or decreases, and why? So now take a look at here for the avalanche mechanism. Let's go to this one first. When PN diode, both P and N are heavily doped. Okay, the P plus N plus, then tunneling mechanism is dominant. Then in this case, as temperature increases, to induce the tunneling mechanism, how much breakdown voltage is necessary? As temperature increases, do we need higher breakdown voltage or lower breakdown voltage? Well, the answer is described here. The VBR decreases with increasing T. Why is that? Go back to the energy band diagram for Zener breakdown mechanism herein. So the physical origin for the Zener breakdown mechanism comes from the electron's movement from P to N. So that is described as tunneling. As temperature increases, this tunneling rate, the number of electrons which has been tunneled through from P to N every single second increases or decreases. Intuitively speaking, more electrons would go toward the N side as temperature increases. That's true. So as temperature increases, more electrons available for tunneling mechanism are on our hands, so that less breakdown voltage, less amount of reverse voltage can be necessary. So that's the main reason why breakdown voltage decreases with increasing temperature when tunneling mechanism is dominant. But this tunneling mechanism is dominant only when both sides are heavily doped. Okay, so simply speaking, in summary, P plus N plus diode tunneling mechanism is dominant. So as temperature increases, more electrons can participate in going through from P to N. I mean, the more electrons can tunnel, so that the breakdown voltage should become low. What about the PN diode or PN plus diode or P plus N diode? Since tunneling mechanism can never be happened in those three types of PN junction diode, definitely avalanche mechanisms are dominant. So think about the basics, how the avalanche mechanism can be happened in reverse biased PN diode. And intuitively speaking, as temperature increases, breakdown voltage increases or decreases. Why? So let's go back to the energy band diagram for avalanche mechanism again. Yeah, this. So as temperature increases, think about this electron should be accelerated, and at some point it's going to hit the silicon atom. But as temperature increases, silicon atoms would vibrating up and down more and more. So before arriving at this point, the electron would be hit the silicon atom at this position. Then the amount of kinetic energy that this electron has lost is much smaller than the kinetic energy that this electrons has lost. I mean, the scattering event would more frequently happen at high temperature. At low temperature, the silicon atom would be kind of frozen out, relatively frozen out. So silicon atom vibration would be minimized, so free electrons can move forward more. So scattering event would be uh, least happen, so that uh, when the electron has hit the silicon atom, the kinetic energy that that electron would lost is huge. I mean, as temperature increases, more frequently the scattering event would be happened. Then the electrons which has been accelerated from scattering event A and scattering event B, the acceleration would not be happened too much, so that the kinetic energy that electron has gained from scattering event A to scattering event B is not too much. But the kinetic energy should be at least the minimum requirement for occurring the avalanche breakdown mechanism is, as I told you, 1.5 times Bank of energy. So you may think that, aha, then much higher band bending, more band bending would be necessary to induce avalanche event. So like that. Then, even though scattering event has been more frequently happened, but due to the increased more band bending, the kinetic energy would be, the lost kinetic energy should be higher than 1.5 times Bang energy. So as temperature increases, because this scattering event would be happened more, in other words, the mean free path length has been shortened out, So more band bending is necessary to meet this requirement for inducing avalanche breakdown. That's the reason why as temperature increases, we should increase, we should apply more negative bias to get to the breakdown voltage. Okay. Okay, so that's all for the lecture note number 16. And here are summary notes for your information. So please take your time and to review all the materials that I've taught in this movie clip. And in the next movie clip, I'm going to explain some deviations from the ideal current voltage characteristic. So maybe the forward bias regime and reverse bias regime. So in those two separated parts, I'm going to tell you what kind of deviations would be happened from the ideal diode characteristics. So thanks for your attention and see you in the next movie clip. Bye bye.